Excellent. So yeah, it is our pleasure today to have Kyle Kremer as a colloquium speaker. Kyle is currently a professor of physics and data science at New York University and a visiting scientist at Meta AI. And in July, he will become the incoming director for the American Family Insurance Data Science Institute at the University of Wisconsin-Madison. So Kyle obtained his PhD in physics from the University of Wisconsin in 2005. He was awarded the Presidential Early Career Award for Science and Engineering in 2007 and the National Science Foundation's Career Award in 2009 for his work at the Large Hadron Collider. And he developed a framework that enables collaborative statistical modeling, which was used extensively for the discovery of the Higgs boson in 2012. And his current interests are at the intersection of physics, statistics, and machine learning. So today we are excited to have Kyle telling us about vignettes in physics-inspired AI research. I will ask you to please leave questions for the end of the talk with the raise hand button in Zoom, unless you have questions that are really needed for clarification. So Kyle, welcome to the IAIFI.
Well, thank you very much. That's a pleasure to be with you virtually, and thank you very much for having me. I thought a little bit about what I wanted to do with this talk, and it's hard to focus on one thing, so I sort of spread it around a little bit. And some of my high-level point is a bit meta, so to speak. Anyway, so I will take it away here. I first like to start by thanking my collaborators. This isn't everybody. I have a lot of different projects recently, but in the last few years, I've been collaborating with physicists of different types than I would normally work with, machine learning researchers, applied mathematicians, and it's just been a wonderful period of intellectual growth, and it's been a lot of fun. And I guess with the transition to my job as the director of the Data Science Institute, the scope of the things that I'm thinking about is just kind of continually expanding, which is fun. So I wanted to share with you sort of some of the things that are in my mind with that kind of background. So I'll start by I think, obvious statement that physics and AI and machine learning is a pretty hot area. I think oftentimes what I see in different workshops that are happening, around the world, is that this interaction is often framed in sort of one of two ways. There's sort of machine learning for physics and physics for machine learning. And so what do I mean by that? Well, machine learning for physics is, I think, fairly straightforward. There are more examples than I could possibly, cover, examples of how machine learning is being brought to bear on physics problems, particularly in experimental, physics, but also in theoretical physics. And you see there a spectrum of what that looks like that goes from, really using essentially off-the-shelf machine learning techniques to things that involve much more, custom solutions. And I just, highlight a few of the IAIFI colloquia recently that are kind of roughly in the machine learning for physics direction. Some papers. There was, for instance, a big Higgs machine learning Kaggle challenge a few years ago, which I think was one of the largest Kaggle challenges in history. And that was really, come with your machine learning tools and try to solve our physics problem.
But not the boyfriend. Okay,
I'm going to keep going. The other sort of side of the coin is people that are bringing, the tools that have been developed primarily in theoretical physics, for instance, in statistical mechanics or quantum field theory, to try to help understand, machine learning, in particular deep learning, in some way. And so here you see, again, two of the recent colloquia that IAIFI had, as well as some, other people working in IAIFI, Giorgio Parisi, who just won the Nobel Prize, for instance, contributed techniques, for instance, this replica method, which are techniques from physics that are being brought to bear on understanding how it is what the dynamics of trying to train some very, very expressive model like a deep neural network looks like. And so these are interesting, and I think these are both interesting, but I want to sort of take a slightly different angle today, is that there's this point that's made and it's advocated by the National Science Foundation, which I actually agree with. And there's an article by Donald Stokes that takes out this point of view, which is that in addition to sort of pure basic research, where you're not really worrying about, a particular application in mind. So that might be like pure mathematics or something like that, or pure applied research, where you're really trying to solve a particular problem. There's also this so-called use-inspired research. And the idea here is, essentially the claim that many foundational advances are often inspired by, starting with some kind of applied research context, and then the peculiarities of the kinds of problems that you run into, and the kind of constraints that you're forced into when trying to solve that applied problem often then end up bubbling up and generating new ideas, new foundational approaches. So you have this kind of, pipeline that goes from the applied direction into the basic direction. And I think that this is important to recognize and to develop like some language about, because oftentimes, I don't know, especially when trying to engage with machine learning researchers, some people are fine with working on purely applied problems, but many are interested in sort of foundational advances in machine learning. And so unless you can kind of give a credible story for how, the process of working on some of these problems might lead to foundational advances in their area, it can often be hard to engage. And I think one of the ways that I think of this is the sort of phrase that reality is stranger than fiction. If you just try to work in a vacuum and think about what's an interesting theoretical construct, you don't have a lot of prompts, and you're kind of used to thinking about the things that you usually think about. But when you tackle some applied problem, you get all sorts of constraints that you might not expect, and that often just sort of helps generate new ideas. So if we talked about the kind of off-the-shelf use of machine learning for physics, I would put that in this applied, quadrant down here. Using physics to understand the theory of deep learning, I would put kind of up here in the top left. And then I'm going to make a slight distinction between two different things. What I'm going to call physics aware or physics informed machine learning. So these are things where you're really like trying to solve an applied problem, and in the process of doing it, you want to incorporate your physics knowledge and somehow incorporate that into the models that you're developing, or into the solution in some way or another. And then physics inspired approaches, and the difference I'm making here is I'm using physics inspired to refer to really more general techniques that can be used outside of the context of the original application, that were just they have legs on their own, but they were inspired from some original physics problem. Okay, so I will give some examples of that later. Now, oftentimes in the process of developing one of these sort of physics aware models, you might be first trying to incorporate your domain knowledge or physics knowledge into the problem, and in the process you might start to abstract things away or make some observations that are more general, and that might lead to some physics inspired approach. But there are other pathways as well that you'll see where sometimes just by formulating the problem and trying to kind of formulate the problem in a slightly, abstracted way, and try to, isolate and identify what is it that's interesting and different about this problem than other problems that you've seen, that might just go directly to some kind of foundational advance, which is still inspired by physics, but it doesn't necessarily go through the pathway of trying to incorporate some specific physics domain knowledge. It's really just in the problem formulation. So I'll give some examples of these, and hopefully it won't seem so high level and meta. But why am I focusing on this? So I think, part of it, part of the takeaway message that I have to this audience is that in addition to the personal joy that we have as physicists and the benefits to society that, doing both, basic and applied research there's also just a lot of value in sort of producing and generating and exporting all these different kinds of techniques for the broader world to use. So it's some sort of like intellectual form of technology transfer. And I think that it really, behooves the field of physics. Yes, I said the word behooves, to try to do this deliberately. And if we want to do it deliberately, it may require adopting some unfamiliar language. We may try to speak the language of statistics and computer science and the notation that you see there more than what you see in physics. It may involve trying to avoid physics jargon that your collaborators may know very well, but which cause a barrier to trying to transfer these ideas outside of our field. It may require publishing in unfamiliar venues, which as a personal matter, maybe doesn't really matter. As a field, it also may involve recognizing the value of those publications by our collaborators, especially during like, tenure and promotions time. And the other thing that I see is like a friction to doing all of this is that oftentimes, if you want to try to abstract your what you're seeing in your physics context to something that might be more useful, you might have to give up some aspects of the problem that are important to you, but are kind of like get in the way of an effective abstraction. So we have to get some level of tolerance to the fact that we might abstract the problem setting in some way that's portable, but doesn't capture every single aspect of the physics problem. Okay. So why do this? Well, I think part of it is it aids in building collaborations with our methodological friends. It avoids siloing and stagnation. I will say that my observation in some fields that are a bit siloed is that they've been thinking about the problem in a certain way for a long time, and a lot of the like fundamental assumptions really need to be revisited. And other fields with structurally similar problems have a different set of assumptions. And oftentimes progress happens when those fields like talk to each other and revisit those assumptions. And that's what I'm referring to as sort of siloing and stagnation here. It also, I think, all of these things about publishing in different venues and adopting this different kinds of language and things like this also really facilitates importing good ideas from other fields. And then this is the last part, which is really kind of like funding related, but I think it's real, is that doing this sort of bolsters the real and perceived value of funding physics research in the first place. And physics research funding is not terrible, but I think we've seen cuts, and it's difficult. And I think that AI and machine learning is really one of the big opportunities that we have as a field to sort of make our value clear, and that will hopefully help so that things like SNOMAS and the decadal survey are not a zero-sum game, but more of a expanding our ambitions. Okay, so with that, before I get into some of the examples that I wanted to share, I'm going to just talk a little bit about the machine learning community. And I sort of titled this section Impedance Matching with the Machine Learning Community, because at least when I first started trying to engage machine learning researchers, and I've seen this pattern play out with friends of mine, is that oftentimes the initial engagement is like, we're trying to solve the mysteries of the universe. These are by far the coolest possible problem that anyone could ever have. So of course you're going to like want to spend your time as a machine learning researcher trying to help us solve our problem. But there are a lot of really interesting problems out there, and that general approach to trying to engage is often not very successful, I would say. So I think what's important is for us to be able to communicate what is it that's interesting about our problem from their point of view. And so to do that, that requires having some sense of what are the interesting questions in machine learning, and what are people debating now, and what's the kind of modern picture. So I'm just going to sort of make some observations, quote some people to try to give a little bit of context for the latter examples. So first, I'm just going to start with sort of the pendulum swinging. So going back, in time a little bit and thinking about how physicists have traditionally solved problems and made progress. The traditional, approaches in physics, especially when you're talking about like, say, experimental data analysis or something, the data analysis is very handcrafted, based on a lot of expert knowledge, theoretical insight. And that has served us very well. So I'm not making fun of it. That's how we've made progress as a field. But it's it's been sort of on one extreme. And what's happened, in the last decade or two was with the sort of rise of big data at first, I would say, and then later deep learning. There was just kind of this big push towards sort of throwing away a lot of that, essentially. So on the machine learning side, there's sort of eschewing feature engineering. A big emphasis on what's called end-to-end learning, where you sort of take out all the intermediate steps and try to just sort of take in raw data and output like, decision like, is there a Higgs boson or not, or something like that, without all of the intermediate stages that we typically would do. And there's a lot of emphasis on this phrase data-driven, which to me is a relatively hollow term without giving, some more more meat to what's meant by it, but it's thrown around a lot. But to give a little bit of a feel for where that's coming from, here are some papers or some articles maybe you've seen before. So this is back in 2008, this kind of absurd claim about the end of theory and how the data deluge makes the scientific method obsolete. But this is where a lot of this is coming from. Here's a quote from Peter Norvig talking about to play on the quote by Box saying all models are wrong, but some are useful. Here he's saying all models are wrong and increasingly you can succeed without them. The point being basically if you have enough data, maybe you don't need essentially theories or models, you can just kind of go straight to solving problems. But what we're seeing now, I think, is a bit of the pendulum is swinging back a little bit from the pretty extreme form of lots of data, end-to-end deep learning, and there's an increased appreciation of some sort of hybrid approach. So you're seeing some pushback within the AI and machine learning community on the very data-hungry end-to-end learning approaches. We see sort of increased appreciation of the value of domain knowledge and this phrase that's called inductive bias, which basically means incorporating something about what you know into the way that you're solving the problem, and the way that that is incorporated. I mean, the reason that the term bias is used is that if you've just sort of made no assumptions, then you're not interjecting any of your sort of like say theoretical bias. But it's also, there's a sort of no free lunch theorem. If you don't assume something, you're basically you're never going to win out in the end. So as you start to kind of add a little bit of structure, which might be very soft at first, then you can sometimes see really big gains. So for instance, convolutional neural networks sort of encode some notion of translational symmetry of your images. And that one piece of inductive bias really helps significantly in terms of the performance and like computer vision tasks. Okay. Now this is a text-heavy slide. I'm not going to read it all, but it's from a NeurIPS workshop that I participated in December. It was hosted partially by Josh Tenenbaum, who's one of the kind of leaders in this sort of way of talking about things. But the workshop was about physical reasoning, and this point of view is coming a little bit more from the cognitive science direction. But you see, I just put in bold various things here. So you see, one, it's being framed in terms of like, human reasoning or even physical reasoning, and basically pointing out that even the best artificial intelligence systems are really like nowhere near, say human level intelligence for a number of different tasks. And then, also making the connection to the physical sciences. You see the role of inductive bias being really important. You see terms like interpretability, things being sort of plausible, and again, you see some criticism of end-to-end neural architectures, and compared to approaches that have some more structure to them, and so they talk about various different buzzwords and things here. This is Peter Battaglia was part of Josh Tenenbaum's group back in the day, and he's now at DeepMind. He's a friend of mine, and I really like the way that he presents a lot of this work. But he makes the point again, kind of the message from human cognition, and I think for a physicist that a lot of this will resonate. That richly structured models of objects and their relations are powerful tools for reasoning about and interacting with the world. Sounds good to me. The idea that intelligence is about model building, not just recognizing patterns. And then this idea of combinatorial generalization via abstraction and compositionality, the infinite use of finite means. Basically, and that's certainly something that we see with the reductionist picture of, in physics, like we have the basic ingredients of, say, fundamental particle physics, which get rearranged in various different ways to introduce all of the complexity that we see through this kind of compositionality. So this is a slide again from Peter. The text is mine. So the point that I would say is that physicists have a lot of insight about the data generating process. I think what's important is to think about how the data came to be, and that's very natural for physicists. I think if you're looking at an image of the galactic center, you can imagine some star or some radiative transport or something like that, and then particles streaming through the galaxy and being bent by magnetic fields and all of these things. It's very easy to tell a story about how the data came to be, including the passage through the atmosphere and through your instrument and Poisson shot noise and all of these kinds of things. It's very easy to tell a very rich story about how the data came to be. Here, these are very kind of simple examples. And this kind of thinking is what motivated, for instance, a lot of the work with graph neural networks. And I'll also point down here this idea of like here you see a sentence being parsed, a parse tree. I'll give an example of something like that later as well. Okay. Now this is a quote from Yoshua Bengio, who is well known for his role in fundamental deep learning advances. And so here you see this kind of question. He's saying, what if the models had the right causal structure? And he's making this claim, which is maybe written in language that's not so familiar for a physicist, but he's like, under the hypothesis of independent mechanisms, that's like language from causal inference, that you basically have lots of some sort of mechanism that happens sort of locally, if you want, and small changes across different distributions, that'll a smaller sample complexity to recover. So sample complexity basically referring to how much data do you need, and to recover from distributional change, that would be somehow something like, if you're taking pictures and you want to identify cats versus dogs and the lighting conditions change or something like that. And for a particle physics example, it would be something like, the calibration of a part of your detector changes or something like that, that changes the distribution of the data a little bit. And so if you could do this, if you had the right causal mechanism, the sort of hypothesis or claim is that these kinds of machine learning models will be much more efficient and more robust, and that's very important. And you see the discussion on the right here by a lot of big names in machine learning, and they're basically going on and on about this. So this is just basically to say that these kinds of topics are very much in the front of mind for a lot of AI researchers right now. I know that Jan LeCun's going to be giving a colloquium, I think, on April 1st. And I actually stole this, still asked for this figure that I think he likely will show in his colloquium. Jan is not exactly a big advocate of, he likes end-to-end learning. So he's not necessarily a big advocate of interpretability or, adding additional structure here and there. But he does agree that, that current AI systems are missing a lot of key ingredients, especially when compared to sort of, well, not just human-like intelligence, even the intelligence of like a small animal, like a rat or something like that. And so here he's just talking about, kind of animal-like intelligence, and some model that involves, perception and et cetera. But, having talked to him about this figure, what he has kind of in the back of his mind is thinking about something like an animal that's interacting with the world. And that's a little bit like the context of reinforcement learning, where you have an agent that's embedded in an environment and it's interacting and it's doing something. And that's where you see kind of cost and intrinsic cost happening. Within the literature about reinforcement learning, there are sort of two broad classes. There's what's called model-free and model-based reinforcement learning. And model-free, essentially, you just try to learn by, like playing Atari a million times. And model-based systems is where you inject your like knowledge or your understanding or your model for how the world and the environment around you works. And as a physicist, this is basically like what physicists do, right? We model the world around us, and we use that world model to make predictions about how the environment will respond, what the potential outcomes would be if we took a certain action. And then we use that in the context of planning, right? We try to think about, should I do this or should I do that? I think about what the possible consequences are under the two different cases, and then I choose accordingly, right? And you see here in this quote I took from Twitter, where he's sort of talking about, sort of criticizing reinforcement learning and talking about it again in the context of optimal control and planning. And if you're familiar with things like Markov decision processes and things, this world model basically appears. And to me, I think that from a physicist's point of view, that's very, very important. I think when we think about what we do as physicists making predictions about the world, it sort of fits in this category. Okay, so having said all of this stuff, what I would like you to have hopefully loaded up in your mind is just the importance of these concepts of inductive bias, And then these are some specific types of inductive bias, like things that the structure that you can add to your machine learning model, things like compositionality, how different components are related to each other, the ideas of, for instance, symmetry, causality. Another idea that pops up a lot is scale separation. At different scales, there might be different effective descriptions of the phenomena that you're interested in. And all of these are very comfortable topics for physicists, right? So, and these are kind of at the forefront of what AI researchers are thinking about. So, so when we talk about physics-aware machine learning, where we're trying to inject our physics knowledge into the machine learning models, that's some type of inductive bias that's relevant for whatever physics problem you're worried about. Now, there can be, you can have hybrids, you can have that structure, but still, one of those modules might involve something very complicated, like that your detector, your particle physics detector has a certain module, but the module might be really complicated. So you might model it with a neural network, but you still have the idea that that module exists, right? You can still point to it and isolate it. And so you can combine these two different ideas. And I think that's roughly what's happening on the physics-aware machine learning side. So I'm going to give an example and then kind of elevate from a physics-aware to a physics-inspired story. Okay, so physics-aware. So the example I'm going to start off here has to do with what are called jets at the Large Hadron Collider. This is a picture of an actual collision event at the Atlas experiment. Here's the interaction point. You see sprays of particles coming out. You can tell they've kind of grouped into two kind of columnated sprays of particles, one over here, the other one coming towards us. These are called jets. And you can tell that they're complicated objects in the data. They've got all sorts of things going on. These squares are sort of represent, the height of these, cubes has to do with the amount of energy deposited, and these lines have to do with the presence of a charged particle flying through the detector. So when deep learning was sort of first brought to bear on these types of problems, the way that it was, there's many different problem settings, but one of them will be, you look at this jet and you have a classification problem. You want to try to classify this thing as one of a few different types of a few categories. Oftentimes there's just two categories, and the categories have to do with what the progenitor particle that produced this thing was. For instance, was it a quark or a gluon, or did you make a W boson or a gluon or something like that? So here's an example where you're trying to classify what are called W jets from QCD jets. And if you don't know about it, I don't think it really matters for this, for my purposes. So here's kind of the cylinder of the detector with all the particles flying out. And the first thing that was done was basically to project those particles and the energy deposits into a regular grid. So it's like a cylindrical image that you can unwrap. And then, so you just get something that looks like an image. The pixels here, basically the value in the pixels, essentially the amount of energy deposited. You can see these two things look very similar to each other. If you focus here, you can see there's a little bit more of a hot spot than there is over here. But this is the average of what an image would look like if you had many, you averaged over many such jets. If you look at an individual jet, they look much more like sparse, like a point process like this. So the very first approaches that were used here, unsurprisingly, this was back in 2015, were to use image-based neural networks like convolutional neural networks to try to solve this classification problem. And that worked, surprisingly well, and that kind of got a lot of the field moving in that direction. But when you take a little bit, closer look, the fact that a typical jet looks much more like this, and most of the pixels are totally empty, at least for me, this seemed like a not the right representation of the data. So one of the peculiarities that you run in here is that it's more like a point process or a point cloud than it's like an image, and the number of particles hitting this thing is variable. It's not there, so it's not like a fixed length vector that you can stick into a normal feed-forward neural network or something. Also, the underlying geometry is not uniform at all. This is like a one slice, and this is a different slice of the Atlas detector. So that's another kind of peculiarity we had with this very non-uniform geometry. So one type of architecture that works with a variable number of objects is to consider them like a sequence and use what's called a recurrent neural network. And they're used, for instance, in language, etc. But in a sentence, you have an ordering. And in our case, we just have a bunch of particles. There's no ordering. It's like a set of particles. So a sequence type model also didn't really seem appropriate to me. So I was listening to my colleagues that do natural language processing, and I saw these kinds of diagrams where you take a sentence and there's a parse tree, and then they were using neural networks that had this kind of structure. And I thought, okay, well, to me, the words here look a lot like, the leaves of a tree, and that's like the particles. And this tree that you make is like what you get when you run a so-called jet algorithm that clusters the particles into what are called jets. And so we developed neural networks where we first ran one of these jet clustering algorithms that gives us a tree-like structure, and then we attached neural network components to the tree. It was interesting. I don't know. I still kind of like the model. I'm not going to make any particular claim here, other than it was one of the early examples of what I would call physics-aware machine learning. And I'll come back to this a little bit later. Okay. After this, there were problems here. One of them is that if you move the particles around, like their momentum continuously, at some point the tree will discontinuously change. The clustering algorithm will have some discontinuous response. So we then moved to thinking about it like maybe the particles should be thought of as nodes on a graph. And this was, back in 2016 or something. And this was like right at the very beginning when graph neural networks were first coming out. And so once you have this, like all these particles, you can think of the edge between them can have like a weight, and we have a notion of how far apart these two particles are. And so that can be represented as an adjacency matrix. And so we did some stuff with graph neural networks. A little bit later, there was the idea that, okay, well, since we just have a set of particles and the ordering doesn't matter, we want permutation and variance to be like one of the forms of inductive bias of this model. And so, Jesse and Patrick and Eric, for instance, were working on some models like this. And I think they were also recognizing the importance of permutation and variance. But there was already just recently been a couple of papers that had architectures that focused on that type of structure. And so then this was in 2020. We had a workshop. This was right before the pandemic hit. There's Jesse there. And there you can tell from the size of this, a lot of activity, basically a lot of activity around this like one area of physics aware machine learning for jets. And here is one like kind of review paper that was put together that compared all these different techniques. Again, I don't really want to make a specific claim here, other than there was a lot of activity in physics-aware machine learning, some kinds of, in some cases, the inductive bias that physicists, bring help with performance. One thing it almost always helps with is it reduces the number of parameters you need substantially. So, for instance, these tree-based models have something like 34,000 parameters instead of 1.5 million parameters. And you can train them with much less data. And so if that's what you care about, those kinds of inductive bias help a lot. Okay, now I'm going to move from that to something slightly different. So it's more in the physics-inspired direction. But I will say that there is an alternate universe out there in the multiverse somewhere where physicists were thinking about this problem and basically invented these deep set type architectures and graph neural networks by thinking about the peculiarities of these problems. It didn't quite happen, but it was pretty close in time. There's definitely, you could tell your story that it could have played out that way. Didn't quite happen, but this next one did happen that way. So here the task, again, is kind of related to jet physics. You've got a bunch of particles coming out, and what you want to do is group the particles together if they came from a common parent. So this was a particle that say decayed into these 3 gray particles. This one decayed into the 2 green particles. This one decayed into the 3 orange particles. So that's your task. You have this set of particles and you're trying to group them together in this way. So we started talking to some computer scientists about this problem. And in the process of doing it was basically, let's formulate the problem in some slightly more abstract way. And the point was that, okay, your input is a set of things. And so you can have models where the input is a set and the output is also a set. You can have models where the input is a set and the output are the edges between them. You can have a model where the input is a set and the output is a graph. Or you could have a model where the input is a set and you might have these kind of, the kind of generalization of an edge, which has like three things in it, a three edge. And so this was the sort of how the discussion started. And then you can represent, sets now, basically, if each of these nodes has some data associated to it. So there's n particles and each particle has a d-dimensional vector in it, then the data looks like this. If you want to start making edges, it looks more like an adjacency matrix with some information on the edges. If you want to do these, bigger kinds of three edges and things, it might start to look, more like a tensor or something. And here's a problem that has nothing to do with physics, but fits in this category. I could give you this set of particles and say predict the edges for the Delaunay triangulation. And so the output would be a graph like that. So you can imagine problems that fit in the setting, and this actually happens in computer graphics, for instance. You'd like to solve this problem. So this led to this collaboration with people from NVIDIA, NYU, Weizmann Institute. It was published in ICML. And we came up with this model, which is called the set to graph model. I'm not going to go through it in detail, but basically you start off with your data, and then you do essentially a deep sets like transformation. So that's sort of set to set. Then there's a so-called broadcasting operation that sort of reshapes the data in a certain way. And then you do a point-wise or element-wise, nonlinearity or, NLP or something on that. And you get out a function. And what's interesting is that we have a theorem that proves that this model is universal in the class of set to graph functions. So that's pretty cool. Like, this is why I would call this like physics inspired, because it's totally useful out in different contexts that have nothing to do with physics, but it was inspired by the physics use case. And so we applied it to our physics use case. And so the set of particles come in, and we would like to basically, the adjacency matrix that corresponds to this picture looks like that. And then the model works quite well. It works better than other baselines that we were using in Atlas. So that's that story. Okay, let me check on my time. Okay. I think I have more examples and slides than I'm going to get to, but that's okay. So I'm going to keep going. Hopefully they'll be, sort of interesting. So here's another one. The physics motivation in this case had to do with, it's a particle physics example. It's experimental setup. We, for instance, have a classifier that's trying to classify, it could be like signal, like, is this event a Higgs boson candidate or not? Or is this jet, a W jet or not? Or some kind of classification problem, for instance. And, but we know that we have systematic uncertainties in our experiment. We don't know the calibration constants perfectly. We don't know various things like form factors for the proton. And, there's all sorts of stuff that we don't know perfectly. And from the statistical point of view, I would represent that as a distribution that's parameterized by some nuisance parameters, and those nuisance parameters are continuous, and there might be many of them. So you might have like 5 knobs that control the different ways that the detector can be miscalibrated and the different theoretical uncertainties that I can adjust. And there wasn't really a machine learning technique out there that was appropriate for dealing with such a situation. And so what we came up with was basically, we're going to have the data comes in to a classifier. It's going to make a prediction. Here's called f of x. And what we're going to do is take the output of the classifier and see if we can predict the value of the nuisance parameter. And if we can, then that means that the output of the classifier is sensitive to the nuisance parameter. And if we can't, then it's insensitive to the nuisance parameter. And in statistics, you would refer to that as a pivotal quantity. So we called it learning to pivot with adversarial neural networks. And you have this kind of mini-max setup, like in a training a GAN, if you're familiar with that. The normal training, this is that distribution of the output of the classifier. And you see red, green, and blue correspond to 3 different values of the nuisance parameter. So it's sensitive. And after this adversarial training, it's insensitive, but it still maintains some classification performance. So that was kind of cool. That was back in 2017. Unexpectedly, this got picked up in the context of algorithmic fairness. where you want to, for instance, you have a classifier that's going to make some prediction about, I don't even remember what this example was anymore, but you want say the output of it to be insensitive to sensitive attributes like race or sex. And so, yeah, so in the process of training this, you see at the beginning, the red and the green are, you get different outputs. And in the process of training it in this adversarial way, you get a machine learning model that is insensitive to these attributes you would like to not be sensitive to. So that was kind of cool. It's also been referenced in sort of work related to encryption. Leon Bateau gave a 2019 ICML keynote where he was introducing this idea of invariant risk minimization, which was sort of took this idea to the next level and incorporated ideas of causality. But that was, I don't know, that was cool. And I think a nice example of physics-inspired machine learning. Okay, here's another example. Again, it has to do with LHC data. In this case, what I'm trying to do is take LHC data and predict or measure the value of some coefficients that describe an effective field theory. So I have like the standard model, and then I can have additional interactions, different particle content, and I can expand around the standard model in the language of effective field theory, and I can parameterize those theories with some coefficients, the real valued coefficients here. And if the standard model is true, all these coefficients are 0. And if the standard model is not true, some of them are non-zero. And then at the LHC, we're basically making measurements of these things and trying to constrain the presence of new physics. So if you want to do that, the thing that you run into, you start off with the parameters of your theory. You can write down Feynman rules for whatever theory you want, and do the typical Feynman diagrams. That gives you distributions over parton level momenta. But we don't see quarks in our detector. The quarks radiate a bunch of particles and turn into these jets that I talked about. And then these particles that are stable then hit our detector, and they ionize and they deposit energy and they do all the things they do. And in the process of simulating all of this, you can think of all of, say, the energy deposits on the detector. I don't see them directly. These are what would be referred to as latent variables. They're variables, random variables that I don't get to observe directly. And then finally, I run reconstruction algorithms on the data, and I get observed data, like actual numbers in a file, that I can access. And if I wanted to think about the simulation chain and software, I can think about tools like MagGraph and Pythia and Geant. And each of them you can think of as sampling from these different distributions. And when you put it all together, the Monte Carlo sampling you can think of as basically implementing this integral over the latent space. But this is an incredibly high dimensional integral. Like for one collision at the LHC, this is something like 100 million dimensional integral. So you're not going to do that integral to evaluate the likelihood for one collision at the LHC. So this is what makes this inference problem challenging. This is like the peculiarity that makes this difficult. Particle physicists have been dealing with this for years. Usually what we do is we pick one good variable that, some summary statistic that we know is going to be useful. We run the simulation a bunch and we fill histograms, like the red histogram is like the prediction that we get from the standard model by running our simulation chain. The black dots are the data. And then we do inference using the histogram as a proxy for this intractable likelihood function. Now, the problem with this technique is that it doesn't scale to high dimensions. It works well if you have one good variable to project your data down onto. But if you don't know what's a good variable or a summary statistic and you want to work with high dimensional data, you can't fill histograms in like 10 dimensions, right? So this is a problem. So what we did is we said, okay, well, maybe we can use machine learning to try to approximate the likelihood ratio. So we'll have a neural network that takes in both the data and the value of the parameters, and it will return a likelihood or a likelihood ratio. And we had to invent some loss functions so that when you train this thing, the neural net will give you the desired thing that you want. And then once you do it, then you can use it you can use it to do inference, just like you had a tractable likelihood function. So we did this, and okay, there's various techniques that made this also like much more sample efficient, which I won't go into. But the impact in terms of particle physics was to take, you want these ellipses to be as small as possible. That's like the more precise measurement, more sensitive measurement. So the traditional techniques were like these red dashed lines. These new techniques give you the blue one. So it's like, significantly more precise measurement. So this is great. And so we later, well, in the process of doing this, we realized that this generic problem setting has been, identified before. It's often referred to as likelihood-free inference. I prefer the term simulation-based inference. One particular technique for that is called approximate Bayesian computation. But that formulation is used, for instance, in systems and population biology, computational neuroscience, computer vision, healthcare sciences, etc. But particle physics was not listed in this list here, right? This is back in 2014. So we put some effort into trying to frame the particle physics problem in this language. In 2017, you see the same thing. Several real world phenomena are better described by simulators that do not admit a tractable density. That means the likelihood is intractable. And then now they're giving examples of particle physics, and which is great. A little after that, we wrote a review paper published in the Proceedings of the National Academy of Science. And now we see things like this tool that's being developed primarily by a group that does computational neuroscience, implementing some of these methods that we talked about, using it to study, neuroscience. In the context of astrophysics, we've taken data that simulated data that looks like gravitational lensing to try to probe the mass spectrum of dark matter subhalos. This was worked together with Sid Mishra Sharma, one of the IAIFI fellows, and Johan Bremer, Jaloup, and Yuri Hermans. And here you see, as data come in, we have an amortized, likelihood ratio that as the data come in, we can quickly update the posterior that describes the power law fall off and the fraction of dark matter in subhalos very quickly, which is pretty cool. So these ideas went from particle physics to neuroscience, astrophysics. Here it's being used for gravitational wave astronomy to look at the data coming into the two LIGO detectors and quickly give you posterior distribution on the sky of where this thing came from, so you can slew your telescopes and look for, say, an optical counterpart. This can happen very, very fast. There are other recent works by Sid and myself using this for astrometric lensing and the context of the gamma ray excess and the galactic center, et cetera, et cetera. There's another framing of the simulation-based inference problem where you don't use deep learning to try to learn like a surrogate for the simulator, but you just use the simulator to do the inference directly, but you have to do some special tricks to make that feasible. And so the idea here is that you have the simulator, and as the simulator is running and it's throwing random numbers, it might check a random number. If it's bigger than 0.5, it goes into one subroutine. If it's less than 0.5, it goes into another subroutine. So you have this kind of very highly structured stack trace of the program. And now you have to try to imagine a distribution over stack traces of programs, which is not the easiest thing to imagine. So that's the distribution you want to model. And so what we do is we actually have neural networks that are reaching in and trying to steer the simulator to produce a simulated output that looks like an observation. And if you can do that, then you end up computing the posterior distribution over the latent variables of the simulator given the observation. And so this is not easy. We had to use supercomputers and big, collaboration with lots of people and Intel and NERSC and et cetera. But in the process of doing it, we developed what we called a protocol so that you can take an existing simulator, in this case written in C++, developed over decades, a million lines of code, and then interface it with an external process, which in this case involves some neural networks and things like that control the random numbers inside of the simulator. And what's cool about that is that protocol has now been used, for instance, in the context of global health decisions, COVID, malaria simulations, and all sorts of things like that. So again, the point here is we developed some technique inspired by particle physics, and now is being used in very different contexts. And I think I'm very short on time. I'm going to skip through this example. It has to do with basically, it's again a jet related thing, and has to do with clustering. Basically, we would like to search over or sum over all the possible trees that could give rise to those leaves, because all of this is latent. The only thing we see are the leaves of the tree, but the number of trees that you have on n leaves grows like double factorial. So it's a super exponential combinatorial growth. So if you have 150 particles, there's 10 to the 300 trees that you can draw on it. And so we would like to search through that space to find the most likely one, or sum over all of them to marginalize over that latent variable, which is challenging. In the process of doing this, we developed like a data structure and a dynamic programming algorithm that does this efficiently. It's still exponentially expensive, but it's super exponentially more efficient than doing it by brute force. So, and then we have a series of approximate techniques where you can control the computational, difficulty. And basically we see like, compared to typical physics, like jet clustering algorithms, like massive gains and performance. But one of the things that's cool here is this algorithm has also been used in the context of cancer genomics, and can also be used in the context of phylogenetic trees and things like that. So this was like certainly not expected at the beginning. And this, because of time, I don't have time to talk about it, but there was a really wonderful workshop at IPAN talking about the connection between deep learning and combinatorial optimization. And I was invited to go basically present what I was just showing you there. And at MIT, you have Stephanie Nagilka, who gave just a really wonderful talk, which I highly recommend. But she introduces this idea of algorithmic alignment, which is some kind of specific formalization of what we were talking about with inductive bias, and has some kind of theoretical results in which cases it's useful or not. And one of the things that's interesting in this is that you start to see an emergence of a connection between dynamic programming, which is what we were using, for instance, when I was just showing you this stuff. There's no machine learning here. This is all classical dynamic programming, computer science stuff. But there's an alignment between dynamic programming and things like graph neural networks. And these are some of these like, theoretical results that she referred to. But interestingly, if you, for instance, use something like a deep sets type of architecture, these types of models might not be able to represent these kinds of dynamic programming, problems, but something that has more structure might. And she has this nice line in here that sometimes you actually encode nonlinearities, not in terms of like sigmoid functions, but in the network architecture itself. And that is very much in keeping with what was happening when we did these at the very beginning that I showed you, these tree structured neural networks. It's basically what we're doing. We have some algorithm that runs to build the architecture, and you can think of that as encoding some kind of nonlinearities and imposing inductive bias and implementing this sort of algorithmic alignment idea. So this is, I think there's a lot to pursue in this direction. I won't say more. And then the last thing that I wanted to say is that the kind of probably the ultimate example of physics inspired, machine learning in quotes, is probably Monte Carlo, right? So Monte Carlo, like, okay, it was kind of in the context of like the Manhattan Project and the bomb and everything, which is unfortunate, but nevertheless, coming from kind of nuclear physics, the types of problems that you saw there, and then later in the context of chemistry and molecular dynamics, there's been all sorts of developments coming out and inspired by physics that in terms of just sampling. And for instance, Hamiltonian Monte Carlo or hybrid Monte Carlo has its origins in lattice field theory, and we're basically molecular dynamics has given rise to all sorts of sampling algorithms. Variational inference, which is used all the time, for instance, for like, analyzing topic models of documents and things like that, has its origin in physics as well, in terms of like free energy and KL divergences and things like this. And one of the things that's happening right now, which I think is very exciting, is that, again, motivated by the problem of lattice field theory, it looks like, another big advance in terms of sampling, which is to bring into the idea of these class of models called normalizing flows and figure out how to integrate them into sampling procedures. So in lattice field theory, you have this very high dimensional distribution. You know what the action for your configurations looks like, but you have an intractable partition function, and you want to calculate expectation values of different operators. So Fiala, my student Michael, and Gurtej Kanwar wrote this first paper almost exactly at the same time. Frank Noy's group wrote a paper that was very pretty much the same idea, using normalizing flows. In this situation, what would maybe be like something like topological sectors of a field theory are quasi-stable configurations of a molecule. You have and trying to hop between one mode and the other mode is very difficult because there's a big, how you make that transition is very difficult. And so they're using flows to efficiently sample these kinds of situations. And so it's very similar structurally to what's going on in the field theory problem. In the field theory problem, we have the additional difficulty that there's all sorts of symmetry that you would like to incorporate. So we've done some work to try to incorporate those symmetries. And in the process of doing that, we had to, for instance, learn how to model distributions on tori and spheres, and that ends up being useful in the context of robotics, because when you have like a robotic arm, the state space of where the arm can be is basically described by a high-dimensional torus. So it's another kind of unexpected connection. So that's basically it. I should stop. I'm not going to go through it, but the last bit here that I have is kind of to come back to some counterpoint, is that I just told this very nice story about like physics and physics ideas and how it helps and all these great kind of inspiring stories. But there's also the counterpoint that comes from Rich Sutton, who's very well known for his work in reinforcement learning, called The Bitter Lesson, which I recommend reading. I included it in my slides, but basically it's sort of exactly the opposite point. He's basically saying, he's not saying that they're strictly exclusive, but basically he's saying that researchers seek to leverage their human knowledge of the domain, but in the long run, the only thing that matters is leveraging computation, and that putting effort into exploiting your human knowledge is basically a fool's errand in the long run. And so he goes on, is actually very thoughtful. And I say he likes this eventual success of basically throwing more compute at the problem is tinged with bitterness and often incompletely digested because it's success over the favored human-centric approach. But I think it's important for us to think about this. But I do think that in some sense, if you look at the examples that I gave, they both include some kind of human element in terms of inductive bias and structure and computation at the same time. And so I don't think they're really necessarily at odds, but I was ending here with some debate that you see on Twitter between, luminaries and machine learning, basically saying, that, this bitter lesson here, well, Danilo, who's part of our lattice QCD work, saying, referring to protein folding and lattice QCD and how these are counterexamples to the bitter lesson. And so I think this is maybe a nice thing to end on, which is just saying that here you see the full circle, that the work that we're doing in physics-inspired machine learning is actually now impacting the very high-level debate that's being had by the AI community. And so with that, I will end. Thank you.
Thank you very much, Kyle, for a very interesting and thought-provoking talk. Let's unmute ourselves to give a round of applause to Kyle. And I open the space for questions. Please raise your hand, your virtual hand. Jesse.
Thanks, Kyle. Really great work and always great to hear your perspective. So I'm curious about kind of with this bitter lesson that you ended on and kind of its relationship, let's say, to the sense to graph stuff. I mean, how much of the bitter lesson is just countered by knowing what the input and output structures are? Basically, just knowing what the data structures are, that's actually what the physics inspiration is, or is there something kind of deeper to that bitter lesson that one needs to take into account? In particular, the type of data you have, whether it has any type of structure, that matters, but it matters, kind of at a basic computer science level. But is the point that once I put that in, then there's nothing further to be gained once I have the data structure, or is there some other lesson I draw from it? Does that question make sense?
Yeah, no, I think that it definitely makes sense. I think it's a good example to pick because I think the answer is clear in this case. Like, so in the set to graph thing, you're basically just stating what the domain and range of the function is, right? It's not, and so in that sense, okay, it's ruling out, it has some inductive bias and just that it like has the right API, but it's not like really assuming much else. And the fact that the function is provably universal means that it can model any such function to arbitrary accuracy, right? So in that sense, it doesn't have any inductive bias, right? So it's sort of like the difference between if you just wanted to say model functions in Rn, you have neural networks, you have these sort of universal approximation theorems, which say if you have a big wide neural network, you can model essentially anything you want to whatever accuracy. If you compare that to, for instance, a convolutional neural network, where you impose translational symmetry and things like that, you basically remove lots of possible functions. And so that's a stronger form of inductive bias because you're actually excluding possibilities. So I would say that in that sense, the set to graph model doesn't have a very strong inductive bias. It just sort of forces that it has the right the right format, input output shape. But it does, so then in that sense, its success is not related to that in particular. But you could imagine that if you, at first, you don't necessarily even know how to represent the right input output shape. It's not super obvious how you're going to go about doing that necessarily. So I don't know if that helped. There's also this comment that I think that's made here by Danilo, which is important, I think, which is says, the bitter lesson applies more to domains where domain knowledge is weak or hard to express mathematically. And so I think this is maybe something we have to be a little careful about as physicists, is that in situations like the lattice QCD example, it's a numerical experiment. It's in silico. There's no measurement noise. There's no detector in the way. And so the symmetries are perfect. They're exact symmetries. And so there, you really should expect that imposing those symmetries is going to help. That doesn't necessarily mean when you go to the real world and you deal with cats and dogs running around, that it's going to, that it's much harder to figure out how to formalize or mathematicize the inductive bias in those situations.
So is it correct to say that the low-lying fruit with physics inspiration is just using the correct structures, the correct input and output, but then the next layer really is understanding the underlying models?
Yeah, so I would say if you think of it that way, the first work about, and this is not to poo-poo the work with the image-based jet stuff, but to the extent that it started off as a point cloud and you force it into an image-based representation, that kind of shoehorning it into a different representation, there's at least the opportunity to lose information there and be kind of suboptimal, right? So figuring out how to be able to work with something that natively works in the data format that you have, I think is something that is a form of physics inspired whatever, and in that sense it's kind of low hanging fruit, but it's not a particularly strong form of inductive bias.
Thanks.
Okay, we are running out of time, but if there is any other question, you should, now it's the time to ask. Well, if not, let's thank Kyle again for a very, very interesting talk. Thank you very much, Kyle, and I hope to have you in person sometime soon in the future.
Great. Well, thank you very much. I appreciate it, and I hope everyone has a good day and take care.